Introduction, powers with negative exponents, expanding decimal numbers, laws of exponents, smaller numbers in standard form, comparing very large and very small numbers. Let's say if I ask you, how far is your school from your home? So the distance between your home and your school might be a smaller number, maybe somewhere around 15 kilometers, even if we consider that the school is not very near to your place. So 15 is not a very big number, so it can be very conveniently represented like this, 15 kilometers. Now if we ask you the distance between your city and another city, so let's say the distance between Bangalore and Delhi. So if you compare the distance between these two cities, the number increases. So it might be somewhere around 1700 kilometers. So again, 1700 is definitely a bigger number than 15, but still it is like quite okay to be conveniently represented. So this is also fine. Now if I ask you what is the distance between your country and let's say any other country, for example, we say distance between India and South America. So if you talk about this distance, it might be somewhere around 14,953 kilometers. So you see, gradually as the distance is increasing, the numbers are also increasing. Now if I ask you the distance between your planet and the sun, so distance between Earth and sun, what's that distance? So it is somewhere around 150 million kilometers. Right? So when you look at these numbers, what do you see? First, you talk about 15. Then we spoke about 1700. Then we spoke about 15,000. And then we spoke about 150 millions. So what happens? As the number increases, we see that it becomes very difficult to represent big numbers. Like if I ask you to represent 150 million kilometers in figures, in numbers, how would you represent? You need to write 15 followed by 7 zeros. So that's not a very convenient representation. Now you can even have numbers as big as maybe 150 followed by 15 zeros or 17 zeros or even 20 zeros. So what do we do to kind of handle these kind of scenarios? So the concept of exponents, the concept of powers makes the representation of bigger numbers easier. Now when I say bigger numbers, not only the bigger numbers, even the smaller numbers. For example, so these are all examples which are given to show the bigger distances. Now if we talk about smaller sizes, for example, if I ask you the size of a cell is very tiny, it's microscopic. You talk about the size of an electron, it is again very small. So for very large numbers or very small numbers, the representation becomes easier with powers. Now let's see that how exponent helps. Now let's say that we have a number, let's consider 100. So how can we write 100? So 100 can be very well written as 10 multiplied by 10. We can write it like this. Okay, perfect. Now this can be written as 10 to the power 2. What does this mean? This means that 10 is multiplied 2 times. So 10 to the power 2 is that's what it means. Now you might say that okay, but writing 10 into 10 and 10 to the power 2 both are equally convenient. So why do we need to the power 2? Well, in this case, it might sound like this didn't bring much difference, the concept of power. But as you move on to bigger numbers, for example, you talk about 1000. So then it becomes 10 into 10 into 10. So 1000 is 10 to the power 3. If you talk about 10,000, that becomes 10 into 10 into 10 into 10. That is 10 to the power 4. Now, in similar way, if you talk about a number which has maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros. So that number can be very well written as 10 to the power 10. Now you tell me which is more convenient, writing this or writing this. So definitely writing this is more convenient. So you see that these are kind of easier representation of numbers. So especially when we deal with very big numbers or with very small numbers. So this type of representation is called the exponential form of representation. So these are called exponential form. So when you write any number to the power some other number, so that representation is exponential form. And how do we read this? We read this as 10 to the power 2, 10 to the power 3, 10 to the power 10, and so on. These that represent the power to which a given number is to be raised. So exponents tell us how many times can we use the number in multiplication. Let's take an example. Let's say 2 to the power 4. So what is exponent? So this 2 to the power 4 is exponent. Why? Now, especially this number 4 is the exponent. Why? Because this number represents how many times can we use 2 in multiplication. So if your exponent is 4, that means you need to use 2 4 times in multiplication. So you will multiply 2 4 times. So here 2 is called the base and 4 is called the exponent or power. So sometimes we use the term power instead of exponent. So in similar way, you can think of multiple examples. You talk about 10 to the power 2. Here 2 is the exponent. It means that 10 should be used 2 times for during multiplication. You talk about 10 to the power 1. What does that mean? 10 has to be used only once. Now if we talk about 10 to the power 0, what does that mean? That means that we are not going to use 10 even once for multiplication. So your result would be 1. So because you are not multiplying 10 even one time. So 10 to the power 0 would be 1. So in this fashion, we can represent numbers, especially the bigger numbers and the smaller numbers, as exponents or using powers of numbers. So let us look at this example. Now let's say that you have 1,000 rupees, maybe in the form of some 10 rupees note. So you have some 1,000 rupees. So different ways of representing it. So you have 1,000 rupees. Now if you take one more bundle, now you have some 10,000 rupees. If you increase the amount more, you might even have a lakh. Increase the number more and you might even have 10 lakhs. So you'd see, representing numbers with more zeros sometimes becomes inconvenient. Now, if I suddenly show you this number and tell you how much is this, you actually need to count the number of zeros, units place, tens place, hundreds place, and only then you'll be able to tell whether it is 1 lakh or 10 lakhs or 10,000. But instead of that, if we represent them like this, 10 to the power 3, 10 to the power 4, 10 to the power 5, 10 to the power 6, so that becomes more convenient. So in this fashion, we can make use of exponents very conveniently. Now you might be thinking that till now, whatever examples I have considered, I have only been considering the bigger numbers, very big numbers. So how do we represent the smaller numbers? So basically when we talk about exponents, we can have two types of exponents or two categories of exponents, positive exponent and negative exponent. So positive exponent is all these exponents, those numbers where the power is a positive number, like 2 to the power 4, 10 to the power 2, 10 to the power 1, 10 to the power 0. So these are all positive exponents. So positive exponents help us to represent larger numbers. But when it comes to smaller numbers, we deal with negative exponents. Something like this, 10 raised to the power minus 4, 10 to the power minus 1, 2 to the power minus 6, 7 to the power minus 15. So you see in all these examples, the exponent is a negative number. So this is called a negative exponent. And negative exponent is useful to handle smaller numbers or to represent very small numbers or smaller numbers. So we have already learned about exponents and powers, especially the positive exponents in our previous class, in your class 7th. So this time we will focus more on the negative exponent. So the next question is, how do we read negative exponents? Like we know how to read positive exponents, but how about negative exponents? So let's look at some examples. So if you have 10 to the power minus 5, so this is to be read as 10 to the power minus 5. Similarly, if you have this, how will you read this? 10 to the power minus 2. Yes, this is 10 to the power minus 2, or you can read it as 10 raised to the power minus 2. How will you read this? This is definitely 10 to the power minus 3. What is this? 2 to the power minus 9. This is minus 15 raised to the power minus 4. Thank you. Please negative exponents. Now let's start with simple things. Let's say if I write 2 to the power 4. So what does this mean? This means that 2 is the base, 4 is the exponent, and this means that 2 has to be used 4 times in multiplication. That is, 2 is multiplied to itself 4 times. Similarly, if we talk about 10 to the power 7, this means 10 is multiplied 7 times. So this is what we have learned from the positive exponents, right? Now the question is, what does 2 to the power minus 4 mean? Or what does 10 to the power minus 7 mean? So now 2 to the power 4 and 2 to the power minus 4 definitely cannot be the same thing. So they need to be something different. So what is it? Now let's do this exercise. So we see that 2 to the power 4 is 2 multiplied to itself for 4 times. Now what would be 2 to the power 3? That would be 2 into 2 into 2. What about 2 to the power 2? That would be 2 into 2. 2 to the power 1 would be 2, because 2 to be multiplied to itself only once. What is 2 to the power 0? That means 2 is not at all multiplied to itself. So this is basically 1. Now what are you observing? Now if you look at each step the exponent is getting reduced by 1. So every time the exponent is getting reduced by 1, what is happening on the right hand side? The entire thing is getting divided by 2. So here it was 4 times 2, you divide it by 2, you get 3 times 2. You divide this by 2, you get 2 times 2. Right? So at each step, so when you look at each step, every time your exponent is reducing by 1, the result on the right hand side is getting divided by 2 at each step. So following that, what can you say? 2 to the power minus 1 would be what? So here also you have reduced further by 1 step from 0 to minus 1. So this side what will happen? This will get divided by 2 further. So this will become 1 by 2. Now if I again proceed further and say 2 to the power minus 2. So this is like the next step of this. So in this case, this 1 by 2 will further get divided by 2. That means this will be equal to 1 by 2 into 1 by 2. Right? Similarly, what would be 2 to the power minus 3? Again, this entire thing will get divided by 2. So this will become 1 by 2 into 1 by 2 into 1 by 2. Similarly, 2 to the power minus 4 would be 1 by 2 into 1 by 2 into 1 by 2 into 1 by 2. Now again, if you look at it more closely, you would see this is 1 by 2 to the power 2. Similarly, this is 1 by 2 to the power 3, because you are in the denominator you are multiplying 2 3 times. Here it would be 1 by 2 to the power 4 and so on. So with this exercise, we understand that for any non-zero integer a, for in this case, that non-zero integer is 2. A to the power minus m is equal to 1 by a to the power m, where m is a positive integer. That is, 2 to the power minus 4 can be written as 1 by 2 to the power 4. So now we have found answers to these. That is, 2 to the power minus 4 is equal to 1 by 2 to the power 4. 10 to the power minus 7 is equal to 1 by 10 to the power 7. So this is how we relate negative exponents with positive exponents. Now not only this, a to the power minus m is multiplicative inverse of a to the power m. That means if you multiply 10 to the power minus 7 with 10 to the power 7, what will you get? You will definitely get 1. That's because when you look at these relations, 2 to the power minus 4 is equal to 1 by 2 to the power 4. So if you multiply these two, what will you get? You will get 1. Why? Let's prove this. So the proof of this would be somewhat like this: a to the power minus m into a to the power m. So by the laws of exponents, when you multiply two exponential numbers, the exponents with same base, so in both these cases base is a, with same base, then the powers get added. So in this case, m minus m would be 0, so this would be a to the power 0, and anything to the power 0 is equal to 1. So the product of a to the power minus m and a to the power m is always equal to 1, which proves that a to the power minus m is the multiplicative inverse of a to the power m.